Okay, everybody, back at it. Back to making videos. I'm excited. I've missed it. I missed it. I miss making these. They're good fun. I have actually more than one old CBA student alumnus watching these videos just for fun. Some of my old students who are in similar situations to you, stuck at home and whatever. But today we're going to talk about rotational kinetic energy. So what does that mean? Well, if something is rotating or spinning, right, what's its kinetic energy? Okay, well, let's say it's stationary, right? It's rotating around some velocity, some angular velocity. So I want to figure out what it is. Well, Ke equals 1/2 mv squared, right? Ke, capital K, either way is fine. Where m is the mass of the object, v is its velocity. Now, typically when we've done this, it's been like, a car or something, moving at some velocity in a straight line. This is linear energy, translational, sometimes we call this. Kinetic energy. All right, it's the energy of linear motion, translational motion, meaning like moving from one location to another. Rotational is different, right? This isn't moving translationally. Well, it is a little bit because I'm not doing a very good job. It's rotating with some kind of energy, right? So how do we figure that out? Well, the first thing we do is look at just one mass, one little mass in orbit around some center point, right? Let's say it's moving with some velocity. It's got some mass and it's some radius from the center, some distance from the center of its circular path. So its kinetic energy is 1/2 mv squared. If it's a nice constant speed, we can just plug in the speed there. But what I want to do is I want to figure it out in terms of omega. Rotational velocity, angular velocity. V equals the radius times omega. All right. So let's see here. We've got Ke equals 1/2 of the mass times our omega squared. All right. And now when we do this, square out this business here, we get 1/2 mr squared omega squared. This is the rotational or angular kinetic energy. All right, for one single particle moving in a circle. It's just writing V in terms of omega. All right. Now, this is for a single point mass. Let's add another point mass to illustrate a point here. All right. So let's say these are two masses, both of mass m, and they're connected by some sort of massless rod, right? And this whole system's rotating. It's like a baton twirling or something. All right, but the mass of the rod is negligible. So since they're rotating together, right, they absolutely must have the same omega, right? When things are rotating in a circle together, they have the same omega. Now, they have the same V also in this case because the radius to the center is the same. We're going to look at a solid object like a disk in a little while here, and we'll see that the omega for every particle that makes up that disk is the same. However, the velocities are different because the greater the radius is, the bigger the path the particle has to travel in a given period of rotation. So that's for one mass. Now let's kick this up to two masses. See how we do this. And you'll start to see that, oh boy, there's going to be some sort of integration involved here. Kind of like before. I'm not going to have you do that, though. I don't think it's going to be necessary at this point for the new format of the exam, and it's not particularly fun. But anyhow, two masses now. So the total rotational kinetic energy of this system now, and I'm just going to write K rotational kinetic energy, is, well, we can start off by writing, well, let's just write it out. 1/2 mr squared omega squared, you know, for one of them, plus 1/2 mr squared omega squared for the other one. So these are two different masses. I could call it M1 and M2. R1 and R2, it's the same R, right? They could be different masses. That's no big deal. Let me simplify this a little bit. So the way we write this is 1/2 of basically we factor out, let's say these are, we factor out the things that are the same. We know omega must be the same for these because they're rotating together. The masses could be different, the radiuses could be different. We'll see that in a second. I'm going to up it to 4 in a second. So M1 R1 squared plus M2 R2 squared times omega squared. So it's the sum. Alright, it's like I factor the omega out in front and the 1/2, and then I sum those up. If I bump it, add another mass, I could add like R3, M3, add another one over here, R4, M4. What you end up doing is you just keep adding M3, you keep adding those terms, right? R1 squared plus M2 R2 squared plus M3 R3 squared plus M4 R4 squared times omega squared. Alright, so what it comes out to be is 1/2 times the sum of the MIRIs times omega squared. Alright, and that is our rotational mass or moment of inertia. We figure those out from the table usually, right? For a ring of material, like a hoop, so to say, where the mass is basically all centered out the same distance from the center, I equals 1/2, or sorry, not 1/2, equals mr squared, where m is the mass of the hoop and radius is the radius of the hoop. Alright, so this becomes capital I. So our final equation for rotational kinetic energy that we typically use when we're talking, this is what's called a rigid body. So a rigid body is something that's rotating and not flexing, not bending upon itself. Okay, rotational ends up being 1/2 I omega squared. Alright, so and these i's, right, so we said this was equals mr squared, the disk, right, like a solid disk, is 1/2 mr squared. Alright, sphere 2/5 mr squared, and you'll be given those when you need them. Alright, so that's a basic equation for rotational kinetic energy. There's some more to do with moments of inertia. Alright, I'm going to kind of go through a bit of worksheet 4, the early parts of it, in another video. I've kind of given the background notes that are already on worksheet 4 in this video. You kind of have to go through and fill those out if you want. We have to talk about something called the parallel axis theorem. Alright, so I'll make a separate video for that. That is important for both rotational dynamics, rotational kinetic energy, and angular momentum. It's basically, alright, all those moments of inertia that I gave you, that we give you in the table, the basic three are the hoop, the disc, and the sphere. Well, also a thin rod, you know, like a meter stick being spun around. That's another one. So those basic moments of inertia are usually given to you, but sometimes, you know, it's like, okay, so when I give you that moment of inertia of the disk, it's always been rotated around the center, right? Which is 1/2 mr squared. Well, what happens if you drill a hole in it and you rotate it around some other point, right? It would be like in your PS controllers or Xbox controllers, there's the vibration function. That's what it is. It's like this motor with this weight on it where the rotational axis is offset a little bit and spins it. And because of that rotation, it does this, that mass rotating around it is what causes that vibration of the remote when you have if you have that turned on and you're doing something, right? So that vibration of the remote is coming from that. There, it's kind of cool. I think I have that turned off on my remotes. I don't know, but anyway, how do we deal with that, right? We see that this would actually cause the moment of inertia to increase because more mass is now distributed farther away. It's going to be a separate video. All right. That video was a little rough. Sorry for it. Just getting back at it. Don't have my usual, quickness. But they'll get better as I get back into practice here. All right. So hopefully everybody's doing good. Take a look at this. Going to keep this short. Just the derivation of this equation. We'll look at some examples in a later video. Talk to you later. Bye.